Howdy. So let's do the Force Toolkit with an example. And the example we're going to have is this box. And the box is being prevented from sliding down the incline because of friction. It's at an angle of 58 degrees. And the box has a mass of 8 kilograms. And so what we're going to try to do is we're trying to do the complete force, the free body diagram for this. And so first step is to identify the system being accelerated. We just did. And the second step is to define a coordinate system. And so our coordinate system here is going to consist of the direction of up and down this hill. This direction will be the x, and then this perpendicular will be the y. And so if I just draw it kind of over here at this angle here, and then this must be perpendicular to this here. Okay, so the box itself, I'll just put as a point right there. And that's our coordinate system. And so this will be my y-axis, and this will be my x-axis. Okay, and going back to here, usually the coordinate system is along the direction of motion. And identify forces by drawing a complete free body diagram. And so let's start off by drawing the forces that are involved. So gravity is always the easiest one to just say, okay, it's going to have gravity. It's going to have gravity there. I'm going to put that in black, straight down like that. And I'm going to call that Fg. And you need to know right off the bat that Fg is always equal to mg. Fg is equal to mg. I'm not going to do the complete numbers yet. I'm going to get to that in a second. So what other forces are on there? I'll make this a little bit bigger. The green, is there a force down the hill? Well, yeah, that's gravity, but gravity's not going down the hill. It's going straight down. And we'll talk about the components of gravity later. There is a component of opposing that, though, and it's friction. Friction prevents it from sliding. So friction must oppose. And so the friction has to be this way. And so this here will be our force of friction, and this will be static friction because it is not moving. Kinetic friction is moving, static friction is not moving, kinetic friction is moving. Okay, and then of course it's on a surface, and that's why it's not falling straight down. And so the surface is going to be the normal force. And so this is going to be Fn, the normal force. And these are at a right angle to each other. This is straight down. Now, what angle is this? And so when we look at this angle, here, as this goes down through space here, and this angle here, we have a couple ways to look at this. If I put the gravity straight down like that, then that angle has to be 32 because this is a right angle. So the angle between that and gravity is 32 degrees. And it's not really drawn to scale. This is steeper than this is. So that is a problem of some sorts. The problem is it just doesn't look like it's 32. Okay, so what does that mean? It also means that this one is 58 degrees. Okay, so going from here, this drawing to this is pretty important. It's pretty important that you know the forces that you have and the angles that you have. Now, these are the only real forces that are present in this problem. There is no other real forces present in this problem. However, that's leads us to our next step because this one is out of axis. So this force is out of my axis. I got my x and y axis here, but this one is out of the axis. And really I want to treat everything just in the two axis, the two planes, the y axis, so the white plane, and the x axis, or the x plane. And so if we go back to the next one, it says include a basic velocity and acceleration motion map. Okay, let's do some housekeeping for a second here. So the velocity is 0. It's not moving. And the acceleration is also 0. It's not moving. So it's not moving. That's pretty important for establishing how we're going to proceed with Newton's laws. And so the next point says draw components if off-axis forces exist. Okay, so let's go back here. Now, this is an off-axis force. I'm going to use the color red to show that this one is in the axis of the red. And I'm going to use the color green here to show I'm going to try to kind of capture this into a parallelogram, right? So this actually fits. This actually fits right here in these lines here, and it fits right here. And these components will help make up our force of gravity. So this one here is the component. It could be either this side or this side. This is the component of gravity that we would call Fg. X. This is the component of this gravitational force that is going down the hill. So this force of gravity, is it really going down the hill at an angle? No, it's going straight down. Always, always, always straight down. Is it going, usually the force of gravity is responsible for the normal force, right? But it's not exactly opposing the normal force. So how much of it is going to the normal force? And so that's why we have this idea where this component here is not actually gravity, but we call this the force of gravity in the y direction. This is in this case, it would be the vertical component of gravity. And this would be the horizontal component of gravity. We're going to call this Fgx, which is the component of gravity, which is going down the hill. And we're going to call this Fgy, which is the component of gravity, which is going into the hill. Fgx is opposite of the friction, and Fgy is opposite of the normal force. Let's see what we got next on our thing here. It says if you prefer, rotate the axis. I don't like to rotate the axis because I want to see that it's downhill. It gives me a visual frame of reference. Some students and teachers might want to rotate the axis. You can see that in the later part of the notes. Okay, write it. E equals the sum of the forces equals ma, or the sum of the forces equals 0. In this case, since the acceleration is 0, then we know that the sum of the forces is also 0 because it is in constant motion. It is not moving and it is not accelerating. So the sum of the forces is 0. That means that they should all be balanced. So if the acceleration is 0, then the sum of the forces is 0. Acceleration is not 0, then you must have Newton's second law, which we'll cover in one of the next presentations in a couple days. Okay, and then it says substitute to solve, and so we're gonna go back and we're gonna substitute the actual forces that we get, and we are working in 2 dimensions. And so since we're working in 2 dimensions, we need a x direction and a y direction. Pretty typical for what we're doing right now. And then finally, we're going to substitute, and we're going to solve for all our unknowns. So let's go back and finish this thing off. Okay, so at this point, we have we should start off with what is the thing that we know. And we know that this is 8 kilograms. And so the force of gravity, Fg, would be equal to 8 kilograms times a negative 9.8 newtons per kilogram. And this will give us an Fg of 78.4, or negative 78.4 newtons. Okay, so then continuing on, we look at the relationships between these. I need to find the components of these. And so what I'm going to do is I'm going to write in the x direction, I'm going to write the sum of the forces. That's not green, that's blue. I'm going to write, what did I just do? The x. I'm going to write the sum of the forces in the x direction is equal to 0. And then I'm going to write again, the sum of the forces in the x direction are actually equal to F S plus F FGX. Now, some people will write this as minus FGX because it's a negative, because it's going down. Algebraically, I find that students can get caught with that. Don't change this to a negative until you're ready to substitute. If you wait until you're ready to substitute, it will be easier to come out mathematically. Okay, and this is actually equal to 0. So let's find out what FGX is. So we need to know what FGX is. So FGX, and I wrote that in green. Good. I'm keeping the same idea. So FGX compared to, if we're talking about 58, right? If 58 is our theta, then we're going to talk about FG being mg sine theta. It's the opposite. This is the opposite. And it's the same size as this, right? That is the same size as that. And it actually, we're going to see, is going to come out to be the same size as that because our net force is going to be 0. These both have to be the same size. So anyways, this is the opposite. It's the same size as this shape. So it doesn't matter if I draw it here. I could have actually drawn it here. Wouldn't have mattered. So FGX is going to be equal to, FGX is going to be equal to mg, which is this thing here. This is mg. That's the hypotenuse, times sine theta, which gives me the opposite here. That's my math here. And mg is, by the way, this is fg in the x direction. And so mg sine theta. So that means that my force of gravity in the x direction is going to be equal to whatever my gravity was, which is negative 78.4, times the sine of 58, which is that angle that we have. And so I'm going to get FGX is equal to a negative 66.49 newtons. Okay, so if I draw it over here, FGX is a negative 66.49 newtons. And for some reason, my pen likes to do this. It turned it into a 9. Anyways, so what that is going to mean is that my FS is also going to be a 66.49, but it has to be a positive 66.49 because they are equal and they are opposite, so that they cancel out, so that I have no net force, and so I'm not going to accelerate along the x-axis. Now, I'm going to pause the video, and I'm going to come back to the other part because my next class is actually coming in, so I need to do that. So I will see you for part 2 in a moment. Okay, let's finish this off. So, okay, so we found FG. We found FGX. Now we're going to find FGY. And so FGY is going to be equal to the same idea. It's going to be mg, which is this one here, mg, the hypotenuse, times cosine theta. And so FGY will be equal to negative 78.4 times cosine 58. And did I do that already in my notes? I did. And so that will give us FGY is equal to negative 60. No, that was negative 41. Negative 41.55 newtons. And that's FGY. So negative 41.55 newtons. And then if you look here, the sum of the forces in the y direction, so the sum of the forces in the y direction must also equal 0. And so these two have to be the same, where this is equal to a positive 41.55 newtons. And so this satisfies everything. Everything's known. The one thing I would say in the end is that don't consider this in the end. That's a real force, but it's no longer really considered part of your force diagram, right? So that thing, we're going to get it out of there because we've put it into its components. This green one here and this red one here are taking care of that, right? You can't do both. It's not like this, and this. It's not like 5 forces here. This is either 3 forces that are the real actual forces, or it is the 4 forces when you're considering the X and Y components for the force of gravity. And so that is an example of the equilibrium tilted axis static equilibrium question. So hopefully that works, and then I'll show you a couple others with other questions involved.